All right, let's just jump right in with a question. What actually gives you your weight? I mean, really? Because I'm going to tell you, the answer you probably learned in school, it's not exactly wrong, but it's only about 1% of the whole story. So today, we're going to hunt down that missing 99%. And the answer, it turns out, gets to the very heart of what it even means for something to be solid.
Okay, so let's get into it. The best way to tackle this is to start with what we all kind of know, right? The stuff from our high school science class. We're going to follow that train of thought all the way down the line until, you'll see, we hit a massive contradiction. And I mean truly massive.
So what are you made of? I know, you've heard this before. You're made of matter. But what does that really mean? Like if we could zoom in, way in, past your skin, past the cells, even past the molecules that make up those cells, what's at the very bottom?
Well, we find that pretty much everything we can touch and see is made of atoms. And at the center of those atoms, you've got the nucleus, which is packed with protons and neutrons. For the longest time, everyone thought, okay, that's it. That's the fundamental stuff. But nope, it turns out even protons and neutrons are made of something smaller, these tiny, fundamental particles called quarks.
And right here, this is where things get weird. This is the puzzle. If you were to take every single quark that makes up your body and put them on a scale, their combined mass would only account for about 1% of your total weight. So where's the rest of you? Where is that other 99% of your mass hiding? Because it's clearly not in the quarks themselves. Okay, to crack this mystery of the missing mass, we've got to shift our thinking a little bit. We need to stop looking at quarks as these tiny individual specks and start looking at the things they build together. And that means we need to get to know a whole family of particles called the hadrons.
You've actually already met the most famous members of this family, protons and neutrons. See, a hadron isn't a fundamental particle on its own. It's what we call a composite particle. Think of it like this. A molecule is made of atoms, right? Well, a hadron is made of quarks. It's basically a little bundle of quarks stuck together by, and this is no exaggeration, the most powerful force in the entire universe, the strong nuclear force.
And you know what's really cool? The clue to this whole thing was hiding in the name from the very beginning, when the physicist L.B. Okun came up with the name hadron back in 1962. He took it from a Greek word, hadros, which means large or massive. So even back then, physicists had a hunch that these composite particles were the real key. Hadrons, just by their name, are where the mass is at. All right, so this hadron family, it's not just one big group. It has two main branches, and each one has some really strict rules about who gets in. They're called baryons and mesons. So what's the difference between them? Well, it all boils down to how they're built. Baryons, and this is the group that includes our friends the proton and the neutron, are always made of an odd number of quarks, usually 3. Mesons, on the other hand, are made of an even number, usually a quark and an antiquark. Now, this simple construction rule has all sorts of big consequences for their quantum properties, like their spin. But for what we're talking about today, here's the bottom line. You, me, this desk, the planet, all the normal matter we see, we're all part of the baryon club.
Okay, quick recap. We've met the hadron family. We know about the two main branches, the baryons and the mesons. We've got all the pieces on the board. So now, let's finally solve this thing. Let's reveal the secret of that missing 99%.
So now we can go back to our big question, but we can ask it in a much smarter way. We know a proton is a hadron, specifically a baryon, and it's made of 3 quarks. We also know the mass of those individual quarks is, well, it's next to nothing. So for real this time, where does the proton's mass, and by extension all of our mass, actually come from?
Believe it or not, the answer has been staring us in the face the whole time. It's hidden in probably the most famous equation in the history of science, E = mc squared. What Einstein's masterpiece really tells us is that energy and mass aren't two different things. Not at all. They're just two sides of the same coin. You can think of mass as just really condensed energy. So, here it is, the big reveal. Inside a hadron like a proton, those little quarks are zipping around like crazy at nearly the speed of light. And what holds them together? An immense amount of energy from that strong nuclear force, which is carried by particles we call gluons. Now think about E = mc squared. All that energy, the kinetic energy of the quarks moving and the binding energy of the gluons holding them together, all of that energy has a mass equivalent. And that's it. That's the missing 99%.
Your mass isn't really coming from the stuff you're made of. It's coming from the pure, concentrated energy that's holding all that stuff together. Mind-blowing, right?
So, we've solved the big mass mystery. Pretty cool. But here's the thing. We've really only been talking about the most stable, well-behaved members of the Hadron family. It turns out that protons and neutrons are kind of the boring ones. They're the exception in what is actually a ridiculously wild and unstable world of particles.
See, if you can get almost any other type of hadron by itself, away from the cozy safety of an atomic nucleus, it just falls apart. Poof, gone. And I mean instantly. We're talking about lifetimes so short they're measured in billions or even trillions of a second.
Let's take the neutron, for example. Inside an atom, it seems totally stable, right? Like it's going to be there forever. But if you get a neutron all by itself, it's actually unstable. A free neutron will decay in just under 15 minutes. Now for us, that's not long, but in the world of subatomic particles, 15 minutes is an absolute eternity.
But the proton? Oh, the proton is something else entirely. It's just in a league of its own. You think the neutron lasting 15 minutes is a long time? The stability of the proton is just staggering. We have literally never observed a single proton decaying ever. Ever. Its estimated lifetime is, well, it's a number so big it's meaningless. It's trillions upon trillions of times longer than the entire age of the universe. The proton is, without a doubt, the absolute bedrock of all the matter we know.
And the story doesn't even stop there. The Hadron family keeps getting bigger and weirder. For decades, the rulebook said hadrons only come in packages of 2 or 3 quarks. That was it. But just recently, physicists at places like CERN's Large Hadron Collider started finding things that shouldn't exist. They've now confirmed the existence of exotic hadrons, things like tetraquarks made of 4 quarks, and even pentaquarks with 5. These discoveries are literally forcing us to go back and rethink the most basic rules of how matter itself can be put together.
So where does that leave us? We've found the missing mass. And the answer is pretty profound, isn't it? The mass of the world, the feeling of solidity in the chair you're sitting on right now, the very substance of your own body, it doesn't really come from the mass of your fundamental building blocks. It comes from the incredible energy that's binding all those blocks together. So it leaves you with this final thought. What if the solid world around us isn't really solid at all? What if it's all just beautifully, complexly, and stably confined energy?